Hello guys, what's up? We are back again with another question from our DSA challenge and level up series. So today's question is from the contest, and the question is find subarray with bitwise and closest to k. So let us first understand what the question states. So in this question, we are given an array nums and an integer k, and we need to find a subarray of nums such that absolute difference between k and bitwise and of the subarray element is as small as possible. Okay. So essentially what we need to find is that we need to find the bitwise and of some consecutive elements, which is closest to k, which is what? Which is closest to k. So this is all we need to find it. Let us understand with the help of this example. For example, in this, k is given. So I will start from here. If I do 1 and 2, then it will be 0. Then I will take the difference. So it will be 3 minus 0, which is 3. Okay. So it might be the answer. Then I will go forward and I'll check. I can check all the subarrays. So 1, 1 to 2, 1 to 4, 1 to 5, 1 to 4, 5. So likewise, I need to check. And if I get the answer, then if I get the closest one, then I can return that as my answer. So the most optimal answer will be 0. And then it would be anything else. Then it could be anything else. So the obvious approach or the brute force approach will be to try out for all subarrays. So it would take n square. If we try for all subarrays, then it will be n square. We need to optimize it. So there are two lines of thinking we can think of. The most obvious to me and the most optimized one is to use a sliding window technique. Let us see how it will work. See, you just imagine that there was a problem where we need to find the sum of subarray elements, which is nearer to k. So what we did, we calculated the sum. We calculated. Okay, if this was here, then we calculated the sum. And then when we exceeded the k, then we subtracted it so that we can reach as near to k as possible. Now, this was only possible. We also need to keep in mind when we were sure that if we are okay, if this is my window, then if I am removing, if I am going left, if I am, let us say this is I and this is j. So if I am going from I to j, I am sure that my sum will decrease. I was sure. And if I am going forward with j, then I was sure that my Windows sum will increase. So can I say something like that in this case? Yes, I can say. Why? Because if since there are only positive elements, considered, if I will go from let us say, even if there are not positive elements, and operation will give me the maximum answer as the number itself. That is, if I add two numbers, then it will always give me an answer reduced, or in the worst case equal to the numbers. For example, if I do, let us say 4 and with 4, then I will get as 4. In all the other cases, I will get lesser than 4 because the bits might differ. Lesser than or equal to 4. So I know that if I am going from, let us say, this is my I and this is my J, then I know that my AND will be decreasing. Yes. So I am sure if my AND is decreasing, then if I will move my I, then my AND of the considered subarray will increase. That's it. That's my job done here. So I can apply similar approach to the sum question, but implementation is slightly trickier because in sum we can directly subtract, but here we cannot directly subtract. We have to consider whether that element's contribution is significant or not. For a bit, okay, so let us understand. There are 32 bits. There are, I can say that, 32 bits. Yes. Now, for each bit to be 1, for any bit to be 1, consider that I am considering some ands, then all the numbers should have 1 at this position. Yes. All should have 1 at this position. Then only this position will be a set bit. So I need to create a count. I need to make a frequency count such that if all the numbers are 1, if all the numbers are contributing 1, then only this bit is set. Otherwise, it is not set, even if we are not considering that particular element in the subarray. So let us now see the code itself and let us try to understand. So it is a standard sliding window approach where right is less than n, and we keep on incrementing right until a certain condition, and then we check for left, and then we increment from I or j. You can say anything. Now, let us understand. I will have my right and left initially initialized to 0. Then I will add value to my right. Now, how will I have to make a bit count. Yes, it is sort of a frequency count where I will count the frequency at every location. I will count the frequency of zeros because I know that if the frequency of zeros is 0, that means 0 hasn't occurred there. That means 1 was there. Then only I am sure that yes, there was a 1 at that place. So I will add that value. Okay. So what I will do, I will first of all add value to window. Let us see what this add value to window says is that add value says is that it will check if the bit is 0. If the bit is 0, it will increase the bit count. If the bit is 0, it will increase the bit count. Now again, from this bit count itself, we will calculate the current value by considering those places where the bit count is 0. Because bit count keeps track of zeros. Yes. So we will do it. Now, if the current is less, if the current becomes less than K, because we know that it is decreasing, if the current becomes less than K, then we will try to shift the window rightwards. Then we will try to shift the windows. Yes. I pointer or left pointer rightwards. Now for that, we need to remove. Now, how will we remove? Simple. We will have the number we will go to the frequency array, and what we will do, we will decrement the, just a second. Yes, we will decrement the count of zeros. Okay, it is clear because that element's role is over. Now we will again calculate the current and we will calculate the minimum difference. If the current is equals to K, then we can clearly return 0. Finally, we will return the minimum difference. So yeah, guys, this was all from this question. So we had a sliding window approach. There is an approach having Fenwick tree, or you can say segment tree you can use. And along with it, you can use binary search. That will give you a complexity around n into log n square. This gives you complexity around n into 32 because you are calculating here 32. So, and personally, I felt it was much more obvious. But yeah, this was something trickier part, and that's implementation. If you know segment trees, that one implementation is bit easier. So yeah, guys, this was all from this question. Thank you so much, guys, for watching this video. Just in case you like this video, make sure you hit the like button, press the subscribe button, and share to your friends. Thank you so much, guys. We shall see you.